That was Robert Earl Keen singing The Traveling Storm. And today, as Robert's song suggests, we are going to be talking about weather. And I do realize the irony of an American person coming in and talking with the Brits about weather, because you guys have really perfected looking at weather and describing it and discussing it. But hopefully today, on the wild side, we can talk about some aspects of weather that maybe you haven't thought too much or talked too much about in the past. But before I get to that, before I launch into my scientific take on what's happening outside in the climate today, I want to do a little bit of housekeeping. And the first thing I want to announce is that there is a researcher up at the University of Exeter, at the Troposphere campus here in Cornwall, who is interested in getting your assistance in a research project that she's doing. And she is studying frogs and the diseases that are afflicting frogs in our area. And so she's interested in getting some samples. So if you have any sort of pond or stream or whatever in your backyard, or garden, as I guess you would say here in Britain, then it would be great if you would contact her and allow her to come in and get some samples. And she's not going to hurt the frogs, she's just hoping to get some samples of the organisms that are afflicting them. And her name is Amber Teacher, and I will put her information on the Source FM website so that you can get in touch with Amber directly, or you can feel free to drop me a line and I can put you in touch with Amber instead. And the second thing is also a bit of a favor that I am asking, and also involves getting in touch with me. And this is also associated with the University of Exeter, because I have been asked to come in and help some people who are interested in learning about science outreach and communicating science with the public. And obviously, since I'm here on the radio, that's something that I'm interested in, but I don't know that I'm necessarily the greatest person at it. And so it would be great if I could get your feedback about the things that you like about the show, the things that you don't like about the show. Just basically anything that kind of has to do with what I talk about and how I talk about it and how I present it, what the web page looks like, anything that has to do with the show. Because they want me to talk a bit about doing a radio show and using that as a medium for getting in touch with the public. So any of your feedback on that issue would be absolutely wonderful, even if you have some negative comments to make. And hopefully that will help improve the show as well. So as always, you can go to the Source FM website and visit the Wild Side page, where I have all this sort of information about myself and how to contact me. But I'll also tell you now on the air that you can get in touch with me at caitlin.r.kite@gmail.com, or even through the Source FM webpage on Facebook, or you can also drop us a line through our messaging system. And actually, I don't have the numbers in front of me right now, but that can also be found through our website if you want to visit at thesourcefm.co.uk. Alright, so that is all of the housekeeping that I have to do, and now we can launch into talking about the weather. And today is actually a really good day to talk about the weather, because it is pretty nasty out there, and there's a lot going on, a lot of wind, a lot of rain, which is actually quite interesting. I guess you have to think positively when you're down here in Cornwall, because we have a lot of that sort of thing. And it can get people down, but it is in fact quite an interesting thing to look at outside your window. And actually it's indicative of a lot that's going on in the atmosphere. And that's what I want to talk a little bit about today. So what is behind all of the things that we see when we look out the window every day and see clouds or clear sky or rain or not? So I guess basically the thing that we're asking is, what is weather? And most fundamentally, weather is the current state of the atmosphere. And you can characterize it by looking at a lot of different variables. Things like the temperature, the humidity, so how much moisture is in the air pressure, and kind of just the general activity that's going on out in the environment. And it generally describes what's happening in an area of our atmosphere called the troposphere. And the troposphere occurs just below the stratosphere. Basically, weather is what happens right at that boundary between those two states. So the troposphere goes all the way down to the ground, but most of the weather, of course, is not happening right at our feet. It's happening way above our heads, up in the clouds. So it's approximately 17 kilometers deep, and we're talking about stuff that's happening about 17 kilometers up above us and then affecting us down here below. And I should mention that this does vary latitudinally, so you do have less troposphere up at the poles and more troposphere as you get towards the equator, but 17 kilometers is an approximation kind of around the globe. Now, of course, as you're probably well familiar with the weather, you probably already know that weather events include things like wind and clouds, rain and snow even here in Falmouth lately, fog and things like dust storms. But then there are also less common events, which are kind of exciting but also quite scary and very damaging. And this includes things like tornadoes and hurricanes and typhoons and even ice storms. And some of these are more common in some places than in others. And luckily we don't have to deal with too much except for wind and rain and fog down here, but there are of course places where things like tornadoes and typhoons and hurricanes do happen on a regular basis. Now, weather patterns are primarily driven by differences in air pressure, and differences in air pressure are related to temperature and moisture. And these variations arise because of differences in the angle of the sun, and therefore differences in latitude, because different latitudes get different amounts of sun, and the sun's rays come in at different angles, and also different times of the day and year because of the rotation and revolution of the Earth. So there are variations in temperature between the tropics and the polar regions, and obviously I don't have to tell you that because we know it's much colder up north in general than it is in the center of the globe. And also there are variations that are caused by the movement of air as we rotate on a daily basis. And so as the Earth is going around on its axis, that movement causes the air to move as well. And these two things together give rise to the jet stream. And you hear the jet stream talked about a lot, but you don't always know what it is. Frankly, I didn't know what it was, even though I kind of generally had an idea of the sorts of things that it impacted in my daily life. So basically, the major jet streams, and there are multiple different jet streams, are located near the tropopause. And the tropopause is where the troposphere and the stratosphere meet, so at that place that's approximately 17 kilometers up in the air, as I said earlier. And our jet streams here on Earth are predominantly westerly, so for the most part they're flowing from west to east. However, they can have really complex routes, and the routes can branch, they can coalesce, so they can, after they come apart, they can then come back together, and they can even flow in different directions. So even though you've generally got things going from west to east, you might have portions that are going from east to west. So they can be very complicated, and there are lots of different things going on up there in the air, which of course is one of the things that makes our weather quite interesting at some times. And we have both polar jets and subtropical jets here on Earth, and both of these are found in each of the hemispheres. So there are at least 4 major jet streams that are going on, but there are also lots of more minor things that are happening in each of the hemispheres due to these, this movement of the air as we rotate, and also the variations in temperature. And what happens when you have minor instabilities, or in fact some major instabilities as well, in the jet stream is that we create the weather events that we see predominantly in the mid-latitudes. So things are a bit different up at the poles because they are quite extreme environments, and they can have a bit more stability actually than in these other places because they're kind of exposed to the same conditions for much longer periods of time in any given time of the year. But here in the mid-latitudes we have things that are kind of fluctuating on a much more regular basis, and so it can get quite exciting. Now, the weather itself can also drive variations in solar heating, as well as being caused by variations in the heat from the sun. So things like cloudiness and precipitation can create these zones where the temperature and the moisture can vary along a gradient. And that's one of the things that we talk about, and I'll go into more detail about this a little bit later. That's what we talk about when we have these fronts, is we're comparing these areas that are a bit different from the areas that are around them. And usually it's not just that you have 5 degrees in one place and 10 degrees in another. You have a variation where it kind of slowly changes from 5 to 10 degrees. And those gradients are the things that are quite important in driving the weather. And these differences that we can find in these different areas may arise partly from physical characteristics of surface features. So you know that if you're living here in Cornwall and you're near the coast, that there are often a lot of really interesting and crazy things happening right on the seashore. And that the shore is just one of lots of different types of physical features that can cause interesting weather patterns to happen. Mountains are another one, forests, blocks of ice like glaciers, even buildings. So any kind of physical structure, whether it's natural or man-made, that kind of shoots up into the air high enough or causes a little habitat change kind of in a small area. So a forest, for instance, when you've got all that variation in temperature and airflow because of the activity of the trees. All these little minor climatic habitat differences can drive changes in weather across the landscape. And these variations result, as I said, from things like moisture content, kind of movement of the air, reflectivity of the sun. So a building and a tree would have different amounts of reflectivity, which is one of the things that could drive the weather differences between rural and urban places, and that's something else I'll talk a little bit about later. And also even just the roughness of the surface, so kind of the topography, and that's why you can often have interesting weather happening along ridges and up on mountaintops. Now, weather is not just meteorology, and meteorology is not weather, and you often will hear these kinds of things, these two words and terms related to these words used interchangeably. But actually, so weather is what's happening right now in the atmosphere, but meteorology is the long-term study of the atmosphere. So you're kind of looking at these things in detail from one day to the next and kind of drawing conclusions about patterns that happen over time and these events that happen. So it's not just describing what's now, but all the variations of things that you might ever see. And meteorology comes from the Greek meaning lofty or high in the sky, which is kind of a nice poetic way to think about this particular type of science. And when meteorologists are studying the atmosphere, they're looking at the weather events that can result from lots of characteristics. And those are the characteristics that I mentioned earlier. So things like temperature and air pressure and water vapor. And they're looking at the amounts of these things, the ways they interact with each other, the gradients of these things over space and over time. And they're also studying these on any one of a number of levels. So you might look at local patterns, you might look at regional patterns, or you might even go really big and look at global patterns. And usually when you think about meteorologists that you encounter in your daily life, so people on the TV or on the radio, these are people that kind of look at the local or maybe even the regional patterns. But people who are looking at global patterns are the kind of people that are really important at kind of understanding what's happening with things like the El Nino effect, or who are kind of making contributions to climatology, which I'll talk a little bit about later, because climatology is a whole other issue that's much larger than meteorology. So it's also important to note that meteorology is only one of lots of different fields that are devoted to understanding things associated with the atmosphere, its characteristics, what it influences, what events happen there. And other fields that are quite related to this are climatology, atmospheric physics, atmospheric chemistry, and it's also quite closely related to hydrology and oceanography. So all of these things begin to affect each other and affect the weather patterns that we see in certain places. And all this information can also be applied to other fields in kind of a more useful and utilitarian sort of way. So ecologists use this data when they're trying to figure out why you can find certain species in certain places. Conservationists need to know this kind of stuff, like when we're thinking about climate change. People who are in agriculture or energy production or the military. So all sorts of people can use these data that are collected by meteorologists and people in related fields. So some of the most important things that meteorologists will measure are rainfall, which you do with a rain gauge, movement of wind, which you do with something called an anemometer, humidity, which you do with a hygrometer, pressure, which of course you probably know you measure with a barometer, and temperature. And these can be measured both within the atmosphere, so you can send up, for instance, weather balloons that will measure these things way high up in the sky, or you can measure them here on the surface. Or even better, you can measure them in both places and kind of understand how these measurements in one place will affect the kind of measurements and conditions that you have in another place. And when you're interested in measuring all this stuff on a surface, that's where weather stations come into play, because these will collect information about things like temperature and air pressure and wind speed for over a long term. So you can have data on an hourly basis for days and days and years on end, and then you can begin to understand how all these variables will impact each other and cause the sorts of weather conditions that we see. Remote sensing is also something that's become more and more important over the years, because that allows collection of data from a long distance away. So using things like radar and LiDAR and satellites, we can take these data even as far away as space and then begin to understand the impacts of these kind of minor atmospheric conditions on the weather patterns over whatever scale you're interested in. which actually is an idea that kind of segues quite nicely into my next point, which is that meteorology can be studied over several different scales, as I kind of indicated earlier. So the smallest of these is the microscale, and this is looking at atmospheric phenomena over a scale of less than a kilometer. And when you're looking at the microscale, you're interested in things like individual thunderstorms or local turbulence that you see as a result of particular surface features like a mountain or a very large building. Then you can move up to the mesoscale, and this extends the range from the Earth's surface up to the lower portion of the stratosphere. So that's actually quite a big vertical stretch. Again, that's maybe that whole 17-kilometer region that accounts for the troposphere. So you can look at things on this scale, things that last anywhere from a few hours up to an entire week. And this means you're thinking about events like long thunderstorms, big fronts, big weather fronts that are moving in, cyclones, or other weather systems that are created by large topographical features. So not just a mountain, but maybe an entire mountain range. And now above the mesoscale, you've got the synoptic scale. And when you're looking at things on this scale, you're interested in kind of the large-scale dynamics of major events that don't happen all that often, probably. So things like extratropical cyclones, so cyclones that are happening out of the tropical regions where they're normally found, baroclinic troughs and ridges, and frontal zones, so the things that are kind of moving in to shift weather for a long period of time. And the minimum size of this is the distance between any two surface observation systems. And I know that's a bit vague, but that's because you can kind of study this over a range of distances. And of course, the smallest is the two areas that you have measurements between, and you can scale that up and kind of ignore all of the intermediate places where you're collecting data and just do two extremes from really far apart. So you can have a large array of places that you can measure at the synoptic scale. And this allows you to be quite flexible and understand things that have local effects but also regional effects. So the next, and this is probably pretty obvious, but the next and largest scale is the global scale. So this is looking at weather patterns that influence the transport of heat from the tropics all the way up to the poles. And also it looks at large-scale oscillations of things like the El Nino event and the La Nina event. And this scale is so big that it begins to merge with climatology. And I referred to climatology earlier as something that is different from meteorology. And that's because it's the study of a variety of meteorological conditions in a particular area over the long term. So here you're focusing on just one specific area, and you're seeing in depth how that area experiences fluctuations from one time point to another. And there are people that actually study the climate all the way back to the beginning of the Earth in certain areas. So the very earliest samples they can get from millions of years ago from plants and things like that, so that they can infer what the conditions would have been like in that area to allow those organisms to grow. And then they kind of build on that and look all the way till now and see what sort of fluctuations happened in between. And they also do things like take ice cores from glaciers and from the Arctic and the Antarctic in order to see what sort of little air bubbles were trapped in the ice, and they can collect those air bubbles and look at what sorts of things were in the atmosphere and what that might say about the weather. So climatology is a much larger scale, really, than meteorology, although climatology is large in the sense that it's going over quite a long period of time, but meteorology can be large in the sense that it can go over quite a large period, quite a large area of space as well. So they both are very informative, but about different things. So that is kind of laying the groundwork now, these basic concepts for understanding what it is that we're going to be talking about for the rest of the hour. And I'm going to have a quick break here of Bonnie Raitt singing Storm Warning, and then we'll be back to think about some more specifics associated with weather. And that was Bonnie Raitt singing Storm Warning. And if you are just now joining us on today's episode of Wildside, then you should know that today we are in fine British fashion talking about the weather. And before the break I was talking about kind of the terminology and kind of the background basics that you need to know to understand weather, and how weather relates to meteorology, and how meteorology relates to a lot of other different fields, and why it's all interesting and important. And now I'm going to answer some of the specific questions that I had about weather and that you might have about weather, because we often see what's happening outside and we kind of chat about the weather, but we don't really know why it is that we're experiencing the things that we're experiencing. And the first thing that I was interested in knowing is how moisture and temperature are related to air pressure. And I think the best way to understand that is to think about low pressure areas and high pressure areas, which are things you often hear talked about on weather forecasts. So low pressure area occurs when you've got atmospheric pressure at sea level that's below that of the atmospheric pressure at surrounding locations. And I mentioned sea level because that's just where all these measurements are taken. It's kind of the standard technique. And so basically when you've got one spot that has less pressure than another, then it's considered low pressure area. And that's pretty simple. But the reason that this happens is kind of what is interesting and how you can begin to relate this to the relationships between moisture and temperature and air pressure. So it can be associated with clouds and precipitation, and these things can minimize temperature fluctuations throughout the day. And basically what happens is that you've got a hot surface temperature that is heating the air, well, not really hot, but just, warmer than normal, and it's heating the air above it, and this causes the air to expand and to rise, and that means that it's becoming less dense, because basically it's all spreading apart and pushing away and releasing the kind of pressure and tension in the air from a certain area, and that's why it's less pressure than in the areas around it. And all that is what causes these clouds and precipitation, and over large areas, when you've got these sorts of lows happening, that's what is responsible for things like monsoon conditions, because you have these strange pressure gradients that emerge where it's quite a bit lower in some areas than in other areas. Now conversely, high pressure areas, they're associated with clear skies, and that can mean warmer temperatures when the sun is shining, because the clouds aren't there to cover up the rays, so all the sun's warmth can get through. But then cooler temperatures when the sun isn't out, so like early in the morning and late at night, because once the sun goes away, you don't have the clouds to kind of act as a comforter or a duvet to keep that warm air down near the ground. And you frequently also find high pressure areas associated with light surface winds. And what happens here is that you've got subsidence, and this is a dense aggregation of air near the ground. And that happens throughout the bottom part of the troposphere. And that is because you've got the higher pressure, you've got more of these molecules dropping down and kind of pushing towards the ground, and that's what makes it a different pressure than the surrounding areas where maybe you don't have all of that heavy air that's starting to aggregate down towards where you are. And often as this happens, as the air is sinking throughout the atmosphere, then it will bring down particles with it. And depending on humidity levels, there may also be fog. And so when you have high pressure areas, that's often when you've got fog collecting. And when you've got these particles that are maybe not so good for you, that's one of the things that can create haze that's quite uncomfortable if you're breathing, especially if you're maybe exercising. And so that's why people tell you to be quite careful if you're out in cities near this time, this kind of weather, because you want to be careful when you're breathing, and you especially want to be careful when you're breathing quite heavily. And that's often obviously the case in the summer when it is quite warm. So the lowest pressure ever recorded, just to kind of give you an idea of where these things might vary, was in the western Pacific, and that happened during a typhoon. And typhoons can bring extreme fluctuations, so you can actually go from quite low to quite high very quickly. And certainly this is so low that people are actually questioning it, because they're not really sure if that is something that could actually be achieved on Earth. But the highest pressure ever recorded was in Mongolia, and obviously these are places that are very, very different. So you've got kind of a tropical area and also a very kind of cold, tundra-like Arctic type area. So you can kind of imagine how low pressure things can be found where it's a bit warmer, and high pressure, when you've got those very clear skies, very kind of crystal clear days, is often associated with these environments that are a bit more chilly and kind of more towards the poles. So something else that's obviously quite interesting here in Cornwall in particular is hydrometeors. And you might not be familiar with the idea of a hydrometeor, but basically what I'm talking about is precipitation. So hydrometeors are any phenomena, I guess, that were produced as a result of condensation or precipitation of moisture within the Earth's atmosphere. So precipitation is actually just one hydrometeor, but it's probably the most interesting to all of us. So this is things like drizzle and rain, sleet, and snow, something called graupel, hail, and also virga. So most of those you're probably quite familiar with, but I'll go over a couple of the more rare ones just so you're kind of familiar with the phrase, because it's a bit interesting to think about these strange things that we don't see all that often. So graupel is droplets of water that collect and freeze on falling snowflakes. And so basically you end up with something that's quite like hail, but it's a bit on the small side, and so it's often referred to as small hail. So obviously the meteorologists are quite witty when they come up with these names. The other thing that you probably haven't heard too much about is virga, and this is precipitation that evaporates or sublimes before reaching the ground. And it's most common in desert and temperate areas. It actually happens quite often in the U.S., in the Northwest, in the kind of Pacific area. And virga can change atmospheric conditions in little patches of the sky, and this can lead to something called microbursts. And microbursts are columns of sinking air that result in tornado-like damaging winds. And these can be quite dangerous for planes. And actually, although this sounds like something that you probably are never going to hear about on the news, it's something that I heard about a couple years ago because one of these happened in my hometown. And the meteorologists argued for several days afterwards about whether it was a tornado that happened or whether there were lots of microbursts as a result of virga. And I think ultimately they did decide it was the latter. And it was amazing how incredibly destructive it was. So it did look as bad as if a tornado had gone through. And it took out all of the trees in the town. It crashed people's homes. It damaged the school that I went to. So it is incredibly serious stuff. And when you're up in a plane and you go through one of these, it can cause you to rapidly drop because all of a sudden you don't have, you don't have the same kind of lift that you had before. These winds are pushing against you. So it can be very dangerous, and these things are quite important to know about if they're happening in your area. Now, all of these things are produced, all these things I mentioned, plus the drizzle and rain and all the more familiar stuff, when atmospheric water vapor begins to condense and then fall to the surface under the pull of gravity. So basically you've got these little water droplets way high up in the atmosphere, and they come into contact with each other and get a little bit heavier and kind of sink down, and they come into contact with more of each other and keep sinking, and then finally they become heavy enough that they're no longer able to kind of float up there in the air, and they are pulled to the earth by gravity, and they land on us as rain or snow or any of these other things. So hydrometeors are also responsible for creating formations, so not just the stuff that actually falls and kind of physically moves around and lands down here on the earth, but also stuff that hangs around up in the sky. So that's things like clouds and haze and fog and mist. And these are also known as suspensions. And these don't actually involve water droplets that precipitate the way that rain or snow do, but things that just hang around up in the sky. So formations like clouds and haze and fog and mists. Now, precipitation is responsible for providing us with access to most of the fresh water on the planet. Each year, about 500,000 cubic kilometers of water fall to the earth each year. And this equates to about 990 millimeters of water in each spot that you might measure it. Now obviously there are certain places that get much more than others, but that's what it averages out to per location. Now the next question that you might have is how the air becomes saturated with water to begin with. And this question is really two questions combined. And the first is, how does moisture get in the air to begin with? And the second is, why and how does that moisture then condense into something that falls down that we see? So to answer the first question, moisture can get into the air in a lot of different ways. So you might have little droplets that are carried by the wind, and the wind kind of moves up and then pushes those droplets up into the sky. You might have precipitation or virga falling from even higher up in the sky, way up towards the stratosphere near the edge of that 17-kilometer boundary. And little by little you can have portions from that upper boundary kind of affecting what's happening below them in areas that are a bit closer to us here on land. You can have daytime heating that evaporates water from the surface of rivers and lakes and oceans, and so you get that water droplet moving upwards and going into the atmosphere. The plants will put some water into the atmosphere as they transpire. We've talked about that in the past on the wild side. You might have cool or dry air moving over warmer water, and so picking up some moisture as it moves along. And you might also have air lifting up over the mountains and again carrying some droplets with it as it moves through the sky. And then once it gets up there, the air can be cooled to its dew point, and the dew point is the temperature at which water will begin to condense. And this happens through a variety of mechanisms, and there are four main ones to know about. The first is adiabatic cooling. And this happens when you've got air that rises and expands, and this is caused by convection, and large-scale atmospheric motions that are associated with a physical barrier. So something like a mountain, for instance, and you've got a process called orographic lift that will take that air and move it up over the mountain, and that will cause cooling to happen because you're picking up that cooler air from the high altitude. Then there's something called conductive cooling, where you've got air that comes into contact with a colder surface, so for instance when it's being blown from water onto land. Then there's a process called radiational cooling, which is the emission of infrared radiation by the air or the surface beneath it. And that infrared radiation, of course, comes originally from the sun, and then it's kind of held within that body below, and then that can eventually rise and affect the air. And then you've got evaporative cooling, and this is moisture that's added to the air through the process of evaporation. And condensation involves contact with something called condensation nuclei. So basically you've got these little particles like dust or dirt, and then the little air droplets will come into contact with those, and it's quite cold up there, so they'll freeze together, and then they'll start to pick up more little droplets and more little droplets, and then finally you've got something like a snowflake or a raindrop or whatever the case may be. And that's how you can eventually have water on the surface that ends up in the atmosphere, that coalesces together, and then eventually can be seen and experienced by us in the form of some sort of precipitation. And now it's time for another break, and this time I'm bringing you a very special song. So this is Matreka Berg singing Here You Come Raining on Me. And back in my previous life when I was a singer, this is the song that I chose as my solo in my a cappella group. So it's very near and dear to my heart, and I hope that you enjoy it. And that was Matreka Berg singing Here You Come Rainin' on Me. And she is introducing our next topic of the day, which is rain. Probably everyone in Cornwall's favorite type of precipitation, right? At least I hope so, because that's what we see the most of. Now, rain is something that we see so much we probably don't even think about what it really is or how it came into being. But it's kind of interesting just to know, because maybe you can look out on a day like this and just think about the process involved in all these water droplets that we're seeing, and maybe not get so down about how miserable it is if you have to go out there. So rain is actually water droplets, which you probably already would have guessed, and these have begun to fuse together from lots of little water droplets. And so what you've really got when you're looking at a raindrop is lots of little tiny bits of water that have come together to form this one single droplet. And this slowly descends through the atmosphere as it becomes heavier and heavier, as I mentioned earlier. And once it becomes heavy enough that it can overcome the resistance of the air beneath it, then it will fall to the ground as rain. And this is a process that's aided by air turbulence, so something that we're definitely experiencing today. And air turbulence will move the water droplets around and smash them into each other, and so they more quickly and more easily form these heavy water droplets that will then fall to earth. So raindrops can range in size from about 0.1 millimeter to anywhere up to 9 millimeters in diameter. So that's why we have a little tiny raindrops. You know, if you're driving in your car, you often will see this. You can have really small ones, or you can have those really giant ones that kind of hurt as they fall on you. And there is quite a big range of size that you can see for rain. And at larger sizes than 9 millimeters, they actually will start to break apart. So that really is the upper boundary of what you can actually have as rain. And the lower boundary is really when you're kind of starting to transfer into something just like mist or haze, where it's just kind of hanging like a really low cloud in the air. Now you might be tempted to say that a raindrop is teardrop shaped, that kind of classical, soft round edge on one end kind of leading up into a bit of a point on the top, but actually that's not what it looks like at all. Raindrops are basically spherical, but as you get quite large ones that are falling and they're moving down towards the earth, and they tend to stretch out a little bit, so they are kind of just like a regular sphere that is a bit longer in the middle, but then still rounded on either end. So the teardrop shape is just kind of a myth, and what they're really known as is oblate. and that's kind of describing that long center section with two rounded ends. Another thing that you rain connoisseurs might have noticed is that the intensity of storms and the length of storms is often quite closely related, but in an inverse fashion. So you tend to have short storms that are very high intensity, but long storms that are a bit more low intensity. And this has to do with the fact that there's a limited amount of moisture in the air, and so if it, if it all is used up all at once, then you're going to have a much shorter storm. But if it kind of is stretched out a little bit, then you can make that storm last longer. So the more intensity there is in a storm, the more the rain droplets are going to crash together and form giant drops that fall down, and then it's going to deplete the moisture content of the air. But if there's a little bit less activity and the rain droplets can just kind of fall nice and slowly, then you might have lots of little droplets that can fall over quite an extended period of time. And so that's why actually it might be to your benefit to put up with quite a high intensity storm, because then it usually will blow itself out in quite a bit less time than those longer storms that can last for days and days on end. Now, another type of weather that's interesting to talk about here is snow. And snow is quite exciting, I think, because it does happen so little down in this area. And I have actually just seen my first Falmouth snow for the first time ever since I moved here about 3 years ago, and that was very exciting for me, even though it did cause an uproar and delay my train and cause me to miss my connection at Truro. It was still very nice to wake up in the morning and see that nice frosting everywhere on all of the roofs. So snow is tiny supercooled droplets that begin to freeze high up in the atmosphere, and as they do this, they start incorporating more and more of the water droplets in the air around them. And so basically snow is just an aggregation of lots of little droplets together, lots of little crystals that form and kind of collect in these nice, beautiful little shapes. And just like rain, once they become heavy enough, they'll begin to fall down through the atmosphere. And as they do this, they begin to collide and stick together and form clusters and aggregates of more and more crystals. And these aggregates are what we call snowflakes. And snowflakes actually can become very large. So supposedly in Montana, in the late 19th century, there were some individual snowflakes that were measured at 38 centimeters wide, although some researchers do question this. But it is true that you can have quite giant snowflakes depending on how far the crystals have been falling in the atmosphere and how much moisture there is for them to collide with and collect on their way down. And the researchers are actually still interested in figuring out how it is that the crystals stick together, because there's very little known about this process, and it's an area of research that's still ongoing. And the shape of a snowflake is something that you hear quite a lot about, because everyone says, well, no snowflake is like any other snowflake that's ever been, and snowflakes are all quite perfect and beautiful and picturesque. And actually it is true that there is quite a whole lot of variation in snowflakes. Now, of course, by chance you might have some that do happen to look alike over time. But it is such an irregular process of just crystals that happen to form and stick together, and that's why you do have a whole lot of variation, because the temperature and the humidity and the movement of these droplets through the atmosphere as they begin to coalesce in crystal form, all of that is going to vary from one snowflake to the next over time, and that's why you do have such an immense variety of snowflakes that can form during a storm. And you can have something called a triangular snowflake that will form at -2 degrees Celsius, and that has to do very specifically with that temperature only. But it's more common that you see irregular snowflakes. So triangular snowflakes would be quite regular because they've always got this kind of triangular symmetry, but irregular snowflakes might have bits that are a bit different than other bits on them, like you couldn't fold them over and have an exact match from one side to the next. And these are often the ones that you don't see photographs, so people will find those nice perfect ones and photograph those, and that's why you tend to think that all of them have that lovely sort of symmetry that you create when you make snowflakes by yourself out of paper, where you kind of cut that very same pattern into all different sides. Another interesting thing to know about snow is that it's not actually white, it just looks white to us. And this is because although ice is clear, the crystals that make up the ice have lots of different facets and imperfections and little micro-topographical features. And this causes them to reflect light. And in fact, they're reflecting all wavelengths of light, which combined equal white. And so that's why we look at snow and think that it's white. Now, just to wind up the show today, I want to talk a little bit about some of the extreme weather on Earth and some of the human modifications that might happen to the weather. So, the weather on Earth is actually quite variable. So over the entire Earth, you can have a variation of about 40 degrees from the coldest to the warmest averages that we see within a given year. The coldest air temperature was recorded, unsurprisingly, in Antarctica at the Vostok station, and this was negative 89.2 degrees Celsius in 1983, which is pretty darn cold. And the hottest air temperature was recorded at 57.7 degrees, and that was in Libya in 1922. This is another one of those measurements that is questioned. Obviously, it was a bit long ago, and some of the instruments may not have been really accurate, but we certainly know that Libya and Africa in general can be extremely warm, so probably 50 degrees or above would not be surprising in those areas. Now, the highest average annual temperature, so not just what we have on a single day, but that are experienced on a daily basis, these are experienced in Ethiopia, and on average, these poor guys have to deal with 34.4 degrees Celsius temperatures. On the other hand, back down in Antarctica at the same station, the coldest average temperature was measured at negative 55.1 degrees. And that is pretty awful, but luckily there aren't really that many people that live down in that area. So probably the more interesting measurement is to think about the coldest average annual temperature in an inhabited location, and this is negative 19.7 degrees up in Alaska. And those are some pretty hardy folks that are going to put up with that sort of weather every year. Now, these are all temperatures that are kind of measured more or less naturally. Obviously, there have been quite a lot of human changes by 1920 and 1983 when some of these measurements were taken. But a lot of people are interested in looking at the sorts of patterns that are going to emerge as a result of human activity. And these sorts of temperatures and patterns are going to change because of the stuff that we're doing to the environment. So, for example, there's something called the urban heat island, which was first studied in 1810. And this is an effect that causes cities to be warmer than the surrounding suburbs and rural areas. And that happens because we've got these materials that we put in that absorb a lot of heat, and they tend to radiate the heat that they have taken in. And also we use a lot of electrics and other things like cars throughout a city, and those will put out heat as they're running. And so actually there is a lot of research that has found that temperatures can be anywhere from about 0.5 degree all the way up to 5.5 degrees higher within a city than in the surrounding area. And also that you can have a lot more rainfall downwind of cities because of how they change the temperature and the moisture content of the air. So rainfall can actually be increased by about 116% within the surroundings of a city, though this is not always the case with all cities. And something else that humans are responsible for, of course, is climate change, which we hear a lot about, and we've talked about a bit here on the show. And this can result from lots of processes. So things like changes in the Earth's orbit, changes in our magnetic field, alterations in the sun's output, volcano activity, plate tectonics, all sorts of natural processes. But anthropogenic contributions are really important, and they're predominantly associated with the use of fossil fuels. And that drives emissions of carbon dioxide and other aerosols into the atmosphere. And also farming practices associated with both crops and animals. Deforestation, ozone depletion, and land use in general are all things that we do that can impact the climate, the temperature of the climate, and the weather patterns that we see there. And this has been tracked using a number of different methods, including ice cores and dendrochronology, so looking at tree ring changes over the years, and also changes in the sea level. And there are lots of different predictions about how this will impact our weather in the future. And of course, it's going to be very dependent on location. Some areas are going to become warmer, others will become colder, some will become wetter, some will become drier. It's going to really fluctuate, and many areas are already experiencing more extreme weather than they ever have in the past. So things like blizzards and tornadoes, and those microbursts that I talked about that occurred in my own hometown. And that's actually one of the reasons I wanted to discuss weather today, not just because we've had some exciting weather here lately in Falmouth, but also because weather is often something that's brought up in the context of the climate change debate. Although it's not so much of a debate in this country because most people do accept it, but it is a debate elsewhere in the world. And it's really interesting to look at these changing weather patterns over a long period of time and think about what they mean not just locally but also kind of globally, and the changes in the processes that are occurring in the environment and how that's going to impact us and the policies that we come up with and kind of whether we have access to certain environments or not. So it is a really important thing to kind of keep track of. And of course, it's also just kind of nice to know about the weather so that you can maybe predict it a bit better yourself, and remember to take your umbrella when you're most likely going to need it, and just kind of understand what's happening out there outside your door. So that is all from me for this week. I'm so sorry I've talked so much. I'll have to play some extra music next week to make it up to you. Just one quick reminder that we do have a professor up at the University of Exeter who's interested in more frogs, and more details about that will be on the Source FM Wildside webpage. And also just to let you know that next Friday,